Hi, and welcome to our second lesson in our second chapter. Today we're going to continue talking a little bit about logic, and our end goal in this chapter is to be able to prove things geometrically. And we're almost ready to begin. We have to introduce you today, or reintroduce you to a type of statement called a conditional. And we have some other vocabulary terms that we'll be talking about today, so this is a great day for note-taking. Lots of vocab, and maybe we'll learn some new words. As you look at the people that are on your screen right now, I'm going to direct your attention to this group up in the corner. They have no question, folks. They are making a statement. And their statement is, we are cool. That's exactly the way that would come out too, I think. A statement or a proposition is exactly that. There are no ifs, ands, or buts about it. It's just a statement. This group of kids, they're a little bit different. They are going to state their belief. If you skate, then you're cool. See, there's a little proviso there. For these people, you can't be cool unless you're a skater. That's called a conditional statement. A conditional. Or think if-then. Okay, that's another way to say, or a definition of a conditional. It's an if-then statement, where the end part of it depends on the start part of it being true. Okay? These folks at the bottom, they're not exactly making a statement about cool. They're making a statement about not cool. And they say, if you don't have an iPhone, then you're not cool, right? Still an if-then. This is a conditional, but it's in the negative, okay? Just different. In an if-then statement, in a conditional statement, the hypothesis is called the if part. That is, for this group of people, their hypothesis is, if you don't have an iPhone. You don't have an iPhone is their hypothesis. The conclusion is what follows if the if is true, or it's the then part. And for them, the conclusion to their statement, if you don't have an iPhone, then you're not cool. You cannot be cool unless you don't have an iPhone. Okay? Kind of weird in the double negative there. You're not cool if you don't have an iPhone. Hypothesis is the if part. Conclusion is the then part. Conditional just means it's an if-then statement, and a statement is just a statement of fact. All right, there's a little vocab to get us started, and let's see what's coming up next. Oh, this looks like lots of wordage. A statement or a proposition is another word for that. May be either true or false, folks. It could be either true or false that group of kids were cool, remember? Its truth or its falsity, kind of an odd word, is called the statement's truth value. Whether it's true or false, that's its truth value. And in math, if a statement is going to be true, it must be true all the time. No exceptions. Okay? Truth in math means it works every single time. A math statement can be shown to be false with what's called a counterexample. And folks, what that means, we kind of looked at that just a tad bit in the previous lesson. A counterexample, that is a case where what should happen doesn't happen. Okay? What should happen doesn't happen. Okay? In the case of our folks back there who are making the statement that they're cool, right? I'm going to go back for just a minute. In the case of these folks, a counterexample would be to find someone who skates but isn't cool, because they fulfilled this part, but what you expect, the coolness, does not happen. Okay? A counterexample is where the hypothesis is fulfilled, but the conclusion doesn't come out the way it's supposed to. That's a counterexample, and we can use a counterexample to show that a math statement is false. And I have something for you to think about. Suppose we think about this statement. A number divisible by 5 is odd. I would ask you to think, is that true? And if it's true, it has to be true all the time. Or is it false? And if it's false, say why. So you start thinking about numbers that are divisible by 5. Well, certainly 5 and 15 and 25 are odd numbers. However, 20 is also divisible by 5, and it is not odd. This statement then mathematically is considered to be false because it's not true all the time. Okay? There are even numbers that divide by 5. And a counterexample might be something like 20, because that's a number divisible by 5, but it's certainly not odd. So we had the hypothesis part of this statement, but we didn't get the expected result. So 20 is called a counterexample. Counterexample. All right, very good. Next, negation. So now we're going to start talking about those folks who said if you don't have a nice phone, then you're not cool. The negation of a statement is another statement with exactly the opposite meaning. Okay, it has to be exactly the opposite meaning. And one way, probably the easiest way to negate a statement is to include the word not in it, right? Because include the word not. And sometimes I'll just say you not the statement. That's what I'm talking about. Put the word not in there. So if we were going to negate this statement, I believe in Santa Claus, the easiest way to do that would be to say I don't believe in Santa Claus. And then I'd say, well, I'm sorry for you. I don't believe in Santa Claus. That's a negation. And a negation gives a statement the exact opposite meaning. I want to go back here for just a moment and look at these guys with their iPhone example. If you don't have an iPhone, then you're not cool. If we want to negate this statement, we have to give it exactly the opposite meaning, and that means that one of these negatives has to change to a positive. If you have an iPhone, then you're not cool. That's the opposite. Change this one. So one not here, one not negates this. And it has to be the not that's in the hypothesis part. All right, let's see. Let's take a look at this example. A polygon with 4 sides is a quadrilateral. What's its truth value? Is that true or false? So if we have a polygon with 4 sides, does it have to be a quadrilateral? Folks, that is true. Okay, that is true because that's exactly the definition of a quadrilateral, a polygon with 4 sides. This is true. So this says rewrite the statement as a conditional, and remember a conditional is an if-then statement. So we're supposed to take this and write it in if-then form. And I'm going to ask you to think about the order of which things are stated in this sentence. It starts with a polygon with 4 sides. It ends with quadrilateral. So the if part of our statement, if, has to include this part. If a polygon has 4 sides. If a polygon has 4 sides. See, the order that statement was made originally is the order that we want to follow here. If a polygon has 4 sides, then it's a quadrilateral. All right. If-then statement, just another, that's what conditional means, if-then. If a polygon has 4 sides, then it's a quadrilateral. We want to talk today and continue our discussion of conditionals, which we just looked at, with 3 statements that are closely related to the conditional. And as we do this, we're going to talk about these statements in words, in symbols, and with an example. So I'd like to have us think about this example to start with. This is a conditional statement. It's an if-then phrase or if-then statement. If a number is divisible by 6, then it is divisible by 3. We have the if part here, the then part there. So hypothesis, conclusion. In words, I should say, in words, if and then is how that statement comes up. I'm using the variable p to stand for the hypothesis. I'm using the variable q to stand for the conclusion. And if you remember, old timers sometimes ask us to watch our p's and q's. I think that's where this comes from, right? P's and Q's, they use those variables to talk about the hypothesis and conclusion in conditional statements in a logic class. So really today is like an introduction to the logic class that you might take in college. In symbols, that conditional, hypothesis, conclusion, is shown with an arrow, and the arrow has several, you can use several words in place of the arrow. Implies is the math word. P implies Q. In other words, if P happens, then Q should happen. P implies, that's an M. Another way to look at that is to just think about the arrow. P leads to Q. Both ways to think about that conditional. So we have it in words, if and then, in symbols with that implication arrow, and our example, if a number is divisible by 6, then it's divisible by 3. All right. The converse of a statement kind of shakes things up. In fact, when I talk about this, I will say that the converse switches. And what I mean by that is it switches the order. In other words, the hypothesis and the conclusion change their locations. So if Q, then P. If Q, then P. That's called the converse statement, and it switches the if and the then. In symbols then, the Q is becoming our new hypothesis and the P is becoming our new conclusion. And if we were going to look at our example, if we take the conclusion part of it and put it up at the start, if a number is divisible by 3, then it's divisible by 6. If a number is divisible by 3, then it's divisible by 6. What do you think about that as I'm writing? Is that true or false? I'm going to let you think about that for a minute. I know this one's true. Can you give me a number that's divisible by 3 that is not divisible by 6? Like 12, it's divisible by both of them. 18 is divisible by both of them. 21 isn't though. This is false, and a counterexample might be 21, and maybe you thought of another counterexample. So the converse of a conditional switches its if with its then. The inverse is another rearrangement of things here. In the inverse, what I like to say is it nots both parts. It negates both parts. And what I mean there is we'd say if not P, then not Q. If P doesn't happen, then Q won't happen. That's the inverse. It negates both parts. Notice the order went back to the original conditional. All of these are ways to arrange that conditional statement. Okay. In symbols, there is a symbol for the not in mathematics, so it's the tilde. Not P implies not Q. And in our situation, we're coming back up here, and we'd say if a number isn't divisible by 6, then it isn't divisible by 3. If a number isn't divisible by 6, then it's not divisible by 3. What do you think about that one? Can we think of a number that isn't divisible by 6 but is divisible by 3? I'm sure we can. We just looked at 21 up there. This statement is false as well. The inverse in this case is false because a number like 15 could be a counterexample. 15 isn't divisible by 6, so this part is satisfied. But it is divisible by 3, which means we don't get what this says we should. See, not all statements have to be true. And in order for them to be considered true, they have to be true all the time in mathematics. And that's it takes a little bit of getting used to. The last of our rearrangements here, our related statements is the way our textbook talks about them, is called the contrapositive. And I want to have you guys think back here. We switched, we knotted. Now we're going to do both. We're going to switch and knot. And I'll bet you that you can show me in words what that would look like. If not Q, because we're switching. Negate and switch. If not Q, then not P. In symbols, the knot of Q leads to the knot of P. In our example, here's where the challenge is. Let's write that sentence for our example. We're switching and knotting. So if a number is not divisible by 3, then it's not divisible by 6. If a number isn't divisible, so we got the negate part, now we got to get the switch part. If it isn't divisible by, we're going to put this part up front, by 3, then it's not divisible by 6. And ladies and gentlemen, what do you think about the truth value of that? I should put that heading up here. We're talking out here truth values, right? Just whether those statements are true or false. What do you think? If it's not divisible by 3, then it's not divisible by 6. Is that true? Like 11 isn't divisible by 3, and it's not divisible by 6. We can't really test every number, but it seems to me like if it's not divisible by 3, then it couldn't be divisible by 6 since 3 goes into 6. This, folks, is a true statement, and I'd love to have you look at the truth values for the conditional, its converse, its inverse, and its contrapositive. Notice that the truth value of the conditional and that of the contrapositive, those are both the same. And that's always going to be the case. Whether they're both true or both false, they have to be the same thing. And that's truth values for the conditional and the contrapositive. The converse and inverse both have the same truth value, whatever it is, either both true or both false. In this case, they were both false. And that's kind of a nifty little factoid to remember. It'll help us out a little bit as we're investigating these claims. So I have another activity for you. We're starting out with a statement, angle A, that's the angle symbol right there, not an L. Angle A that measures 120 degrees is obtuse, and we are supposed to rewrite that as a conditional. So we want to put it in if-then form. Okay? If the measure of angle A is 120, then it is obtuse, and the it that we're referring to is angle A. All right, what do you think? Is that true or false? Is a 120-degree angle obtuse? That's true. All right. The converse, remember the converse switches. So if an angle is obtuse, then its measure is 120. Is that true? If it's not, then we got to be thinking there might be some angles that are obtuse but don't measure 120. And sure, that could happen all the time. In fact, a counterexample might be, say, 95. right? That's an obtuse angle, and it's not a measure of 120. So we have a counter example there. Let's go back to our original conditional, and we'll want to write its inverse. The inverse knots both parts. Okay, so we're going to knot both the hypothesis and the conclusion. Knots both parts. Let's see. If the measure of angle A is not equal to 120, then it is not obtuse. Folks, that's going to be false. In fact, there are many angles whose measures are not 120 that are obtuse. One like maybe 150 could be an example of that. So a counter example, there's an angle that's not, right, not 120, but it is obtuse. We satisfy this part, but not this. That makes it a false statement. The contrapositive does both things. It switches and knots. And as you look at our sentence, it's got to come out something like this. If angle A is not obtuse, then its measure is not or isn't 120. Right? If it's not obtuse, that means it's either less than 90 or more than 180. That certainly can't be 120, folks. That's a true statement. And here comes, just so that we have this in our notes for sure, a conditional and its contrapositive are equivalent. Is a word that means equal, or they're the same. They are either both true or both false. Okay, whichever, they could be either one, but they both got to be the same. It's also true that the converse and inverse are equivalent statements. They also have to have the same truth values, both either true or both false. This is a separate thought, and it's squeezed down here at the bottom of the page, but it is an important one. When a statement and its converse are both true, that is, if it's true going forwards and backwards, right? Because that's what the converse does, is switches. So if it's true going forwards and backwards, you can write that statement. It's called as a biconditional, B-I and then conditional, by joining the hypothesis and conclusion with the phrase if and only if. And you may remember from a previous lesson, the abbreviation for that is IFF. Folks, any mathematical definition can be written as a biconditional. It works both ways, okay? Definition for an even number. If a number is even, it's divisible by 2. If you do the converse of that, if a number is divisible by 2, then it is even. Both of those are true. Therefore, you could write that definition as a biconditional, and it would look something like this. A number is even if and only if it's divisible by 2. If and only if it's divisible by 2. Any math definition can be written as a biconditional. Okay, folks, that brings us to the end of today's lesson. We'll ask you to take a look at the You Try tonight and submit your results for that as soon as you can. I hope you have a good evening.